Hello, class. We are now delving into Chapter 2, which covers set theory. Now, today, we are just going to cover the basic set concepts in order to set this chapter up. So, we do have a long list of objectives here, but many of them are just basic concepts that are fairly easy to grasp. So, objective number 1, we're going to use 3 methods to represent sets. We're going to define and recognize the empty set. We're going to use symbols such as included in and not included in, or a member of or not a member of, depending on the textbook. Apply set notations to sets of natural numbers. Determine a set's cardinality number or cardinal number. Recognize equivalent sets, distinguish finite and infinite sets, and recognize equal sets. So let's first define what a set is. A set is a collection of objects whose contents can be clearly determined. Elements or members are objects in a set. A set must be well defined, meaning that its contents can be clearly determined, and the order in which the elements of the set are listed is not important. Now, there are methods for representing sets. Capital letters are generally used to name sets. A word description can designate or name a set. Use W to represent the set of the days of the week. We're going to use the roster method to list the members of a set. The roster method is similar to like a baseball roster, and you'll see what I mean shortly when we do the actual example. So if we let W define this set, that is the days of the week, using the roster method, which is basically just using these parenthesis style symbols here on either side to include the set, the days of the week are Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. We include them in these bracketed style curly Q parentheses here. That is the roster method, where we just list all elements of the set out within those 2 parentheses there. Now we use commas to separate the elements of a set, just as you would in basic English. Braces, is what this book calls them, are used to designate that the enclosed elements form a set. So this book calls these brackets braces. Let's do another example. So this one says example 1, representing a set using a description. So write a word description of this set. P equals, the members of the set are Washington, Adams, Jefferson, Madison, Monroe. Now, if you're not a history buff here, no harm, no foul. But these are actually the first 5 presidents of the United States of America. So if I wanted to use words to describe this set, I would say the set P is the set of the first 5 presidents of the United States. Let's look at example 2. Example 2 says representing a set using the roster method. Set C is the set of U.S. coins with a value of less than $1. Let's express this set using the roster method. Okay, remember, the roster method uses braces, and then you just express or write out the members of the set. I'm going to start with the smallest one I can think of that is less than $1. That would be a penny. Next, we have a nickel, a dime, a quarter, and we still do have some half dollars. want to finish my roster method with my other brace. So this tells me that this is my set. As you can see, that solution is correct. Now, something that is of note here, especially if you are naming the set using a letter, it is important not to forget the step where you actually set that letter equal to the set itself. Now let's look at set builder notation. W equals the set X such that X is the day of the week. So that's how I typically say it. This one reads out set W is the set of all elements X such that X is the day of the week. So the brace lets you know that it's the set of right here equals here. I think you can pretty much get the first two terms. The set W is, because it's equal to, the set, which is indicated by this brace, of all elements X. This is where this first X comes from. This vertical line here means such that. So all elements of X such that X is the day of the week. So once again, we read this notation as set W is the set of elements X such that X is a day of the week. Before the vertical line is the variable X, which represents an element in general within that set. After the vertical line is the condition X must meet in order to be an element of the set. So let's look at example 3. We want to convert from set builder to roster notation. So let's express this set A, which is a set of X such that all the elements of X are X is a month that begins with the letter M. And we want to write this out using the roster method. Okay, so remember, we're basically converting from the set builder notation to roster notation. Now let's think through all the months. And you don't have to be good at writing this bracket, but I could probably do a little better than that. So let's see if we can. Do I have an erase button? Let's see. Here we go. Let's try to write the roster method a little bit prettier than that when it comes to it. So a little bit better of a handwritten bracket there. Now let's think through the months. Essentially, we're trying to think of all the months that begin with the letter M. Okay. So also important to keep your letter out front to define your set. A equals. Now January is a J. February, March, that's an M. So March is a month that begins with M. April, May, there's another one. June, July, August, September, October, November, December. That's it. Those are the only months that begin with the letter M. This is how I write them with roster method. So once again, our solution, there are only 2 months, namely March and May. Thus, A equals the set March and May. If you remember from our definition of the set, the order does not matter. So, if you were to have written this set May, March, that would have been perfectly fine, acceptable, and correct as well, because orders in sets do not matter, as long as all the correct elements are there. Now let's define the empty set. The empty set, also called the null set, is the set that contains no elements. The empty set is represented by either a set of brackets here, or braces, with absolutely nothing inside, or by the symbol here, which is essentially a circle with a slash through it. So either one of these symbols can represent the empty set. The one we typically see is the circle with the line through it, representing the empty set. So this says these are examples of the empty set. Let's look at this. the set of all numbers less than 4 and greater than 10. That would be the empty set. The reason that would be the empty set is I challenge you to list a number that is less than 4, but at the same time greater than 10. No such number exists. Because there are no such number that exists, and there's no solution to this problem, the answer to this problem would then be that set is empty. There's nothing in it. There's no number that satisfies both of those conditions at the same time. Therefore, there's essentially no solution. No solution means that it is an empty set. So let's recognize the empty set. Which one of the following is the empty set? So this one is a set with 0 in it. Is this the empty set? No. This is a set containing one element. That element is 0. 0 is not empty. It's a completely different concept. Empty means absolutely nothing. 0 is essentially a number. A number is something. So it is not empty if it has 0 in it. 0 is a solution. Empty means no solution. So if we look at B, B is 0, just not in set notation. So if we go with B, that one is also not the empty set. It's a number. It's not even a set to begin with. It is just a number. The empty set is a set containing absolutely nothing. That's why we showed and represented it with empty braces or empty brackets. And the only other way to represent it is the circle with a line through it. 0 and empty set are not the same thing at all. Which of the following is the empty set? We're continuing this example. X, such that X is a number less than 4 or greater than 10. Is this the empty set? Now this is really similar to that other example we went through earlier. Let's click back to it. Right there. But in this first example, there's one slight difference. We used the word and. In this example, we're using the word or. That makes all the difference. When you use an or expression, as long as either of them are correct, either one or the other are correct, then you have a solution. If you use and, they both have to be correct at the same time. That's why the first example indeed was an empty set, but this example with the use of or is not, because only one of those statements has to be true at a time. Or they can both be true at the same time, but at least one has to hold true. So no, this set here contains all numbers that are either less than 4, such as 3, or greater than 10, such as 11. So this actually does contain values here. So it is not the empty set. Let's look at problem D. X such that X is a square with 3 sides. Can you have a 3-sided square? Squares have 4 sides. There's no such thing as a 3-sided square. If it has 3 sides, it might be a triangle, but it's definitely not a square. So, this actually would be an example of the empty set here, because there are no squares with 3 sides. Okay? So yes, this is the empty set here. You could represent it as such. You could say, yes, this set definitely simplifies down to the empty set, because squares have 4 sides, not 3. So let's look at notations now for set membership. The symbol, which is essentially almost looks like a small e, a small capital E here, is used to indicate that an object is an element of the set. Kind of makes sense that it looks like a small e, right? The symbol, element, is used to replace the word is an element of. So we will use this symbol, like I said, essentially looks like a fancy little small capital E, will be used to replace the words is an element of. Now, on the opposite side of that, the symbol with the little e here with a slash through it is used to indicate that an object is not an element of the set. The symbol, the little e here with the slash through it, is used to replace the words is not an element of. So we have is an element of and we have is not an element of. Okay, let's see if we can do this. Determine which of the following statements are true or false. R is an element of A, B, C. The comma dot 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 means this trend continues all the way to Z. So basically all the letters of the alphabet, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. That is our alphabet. Is R contained in that? Is R an element of this set? Remember, this stands for is an element of. Is this a true statement? It is. R is an element of our alphabet. So this is indeed true. Now, remember, when it has a slash through it, it means is not an element of. Not. So, the question here is 7 not an element of 1, 2, 3, 4, and 5? Is this a true statement? This is indeed a true statement. Because 7 is not an element of that. 7 lies nowhere within that set. Therefore, it's a true statement. If we look at the next statement, A such that A, B, so A such that A is an element of A, B, or the set A, B. Is this true? Well, yeah. Is it true? No, it's not true. This is where things get a little tricky. Okay. This is false. And this is one of those trick style questions. The set of A is a set, and the set A is not an element of the set AB. The element A is a set of the set AB. Sorry. So, if you follow through, we're following that what is on this left-hand side, the entirety of it, in order for this to be true, has to be on the right-hand side. That's not true. Only the specific element A is a member of this set, not the entire set of A. A little tricky, I know. In order for this to be true, the set would have to look like this and actually contain the set of A and not just the element A. So, be careful. It can get tricky. So, is the set A an element of the set AB? No, it's not, because the entire set notation is not included on the inside. Little tricky. Little tricky. Let's look at the sets of natural numbers. The set of natural numbers are your natural counting numbers. Your 1, 2, 3, 4, 5, continuing up. Okay, so 6, 7, 8, 9, 10, 11. Essentially all your whole numbers going up from that point. It does not include 0. It does not include negative numbers. It just includes your natural counting numbers starting at 1 going up. The 3 dots or ellipses after the 5 indicate that there are no final element in the set and the list goes on forever. This itself would be what we eventually call an infinite set, and we will hit that definition shortly. Now, let's represent the sets of natural numbers. So we want to express each of the following sets using the roster method. Set A is the set of natural numbers less than 5. Now you really have to read what your question is here. Kind of ties into last lecture, where you really have to read and understand what the question is asking. We're looking for numbers, natural numbers, that are strictly less than 5. So if I try to set this set up, I'm going to say that A equals the set. Now, it's less than 5. Natural numbers start at 1, and they go up. But we want them to be less than 5. So we will stop at the first natural number before 5, because it's not equal to 5, it's strictly less than 5. So the set of natural numbers less than 5 is A equals 1, 2, 3, 4. Let's look at the set B. Is a set of natural numbers greater than or equal to 25. The key here is that not only is it greater than, it's actually equal to 25 as well. So if I'm looking here, B equals the set of natural numbers that are greater than or equal to 25. Because it says the word equal to, I know I start at 25 and then go up because it's greater than. So 26, 27, going up forever, because it doesn't tell you it stops at any particular point, and the natural numbers do continue to go up forever. They wrote theirs with an extra element. I won't say an extra element. They indicated how their list would continue forward using 4 elements. I only use 3. As long as we can indicate what your pattern is and you use enough numbers to do so, you're fine. The answer typed versus the answer written here are essentially the same answer. They have the same number in the set because the set continues forever anyway. It is what we call an infinite set, which definition we will make more concrete towards the end of the lecture. Now, E, the set E, equals X, such that X is an element of the natural numbers. Now, this representation here, this capital N, right here, if you see a capital N, that is an abbreviation for natural numbers. Okay, so X, such that X is an element of the natural numbers, and X is even. Okay, so if I were to write this one out, so I would say something like E equals the set. All right, my first even number. Now, the natural numbers start with 1, and they go up by 1. So 1, 2, 3, 4, 5, 6, that's the natural numbers. We know that. The first even number in the natural numbers is 2. And then I'm going to look at every even number after that. So 2, 4, 6, 8, and then that basically continues forever. That is our set of natural numbers, such that we're only looking at the even natural numbers. Easy enough, right? Starting to kind of catch the concept. So let's look at the table here. So we have inequality notation in sets. An inequality symbol and its meaning is in the first column. The set builder notation will be in the second column, and the roster method will be in the third column. So if we look at this first example, X is less than A is what this notation stands for. Remember that this is the less than sign. So X is less than A. If we were to write this in set builder notation, we would write it X, or the set X, such that X is in the natural numbers, or is an element of the natural numbers, and X is less than 4. Okay. If I wrote it in the roster method, I would write it 1, 2, 3, because those are the natural numbers less than 4. Simple enough. If I had X is less than or equal to A, it would mean that X is less than or equal to. It has this additional part of an equal to sign here below the inequality to let you know that it's equal to. Okay. If I had the set builder notation, X, such that X is an element of the natural numbers and X is less than or equal to 4. So essentially what we're doing here when we get to the set builder notation, here we're not looking at the natural numbers in the first column. We're just looking at the inequality that will be derived into the set builder notation. So we're combining this inequality with the fact that x is in the natural numbers, and that's how we get our roster method here. The difference between this first example and the second example is that it's actually equal to. So that adds an additional element to our set here. Because it's equal to 4, and also less than 4, and also a natural number, it is the set, if we wrote it in the roster method, 1, 2, 3, and 4. If we look and remember that the symbol here means greater than, our set builder notation here is x such that x is in the natural numbers and x is greater than 4. That means basically we're looking at the natural numbers. We're looking at all numbers greater than 4 in the natural numbers. That means we start with 5 and essentially continue upward by 1. So 5, 6, 7, 8, comma, dot, dot, dot to indicate that our pattern keeps going upward. This is greater than or equal to. Just a reminder on what this inequality means. So if I get given a set builder notation that says x such that x is an element of the natural numbers and x is greater than or equal to 4, that means that because of the equal to sign here, I need to start at 4 and continue to go upward in my natural numbers. 4, 5, 6, 7, comma, dot, 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 which means we continue upward in that same fashion. Now, let's look at double inequalities here. So we can basically bound our x on both sides. In this first set here, I have, with my inequalities, just reminding you how you would say this, this is x is greater than a and x is less than b. Or you could say a is less than x is less than b. That would also be correct. If we look at this in our set builder notation and give it some more restrictions, it says x such that x is an element of the natural numbers and 4 is less than x is less than 8. So x is a natural number greater than 4 and less than 8. Okay, so if we look at that, because there's no equalities here, that basically means all numbers between 4 and 8 that are natural numbers, but not including 4 and 8 because it's not equal to. So the first number bigger than 4 is 5. So 5 would be included, 6 would be included, 7 would be included, 8 wouldn't be included because it's not equal to 8 here. If we look at a is less than or equal to x is less than or equal to b, or also spoken, x is greater than or equal to a and less than or equal to b, and I have this in set builder notation, x such that x is an element of the natural numbers, and 4 is less than or equal to x is less than or equal to 8. Because of the equality here, I know that I can start with 4 and end with 8 because of these equal signs, and it includes every single natural number in between. So 4, 5, 6, 7, 8. You can also mix and match here. We can have an equality on one side and a not equal to on the other side, where we have strictly just an inequality. So a is less than or equal to x is less than b. Or a is greater than x is greater than a, greater than or equal to a, and less than b. So we're looking at x such that x is an element of the natural numbers, and 4 is less than or equal to x is less than or is strictly less than 8. So here we have one equality, so we know we can start with 4 because it is equal to there. I can work my way up 5, 6, 7, 8 and stop there because it's less than 8 but not equal to. If I'm looking down here, it could be on the other side as well. You can have a is less than x is less than or equal to b. You can have the set builder notation, x such that x is an element of the natural numbers, and 4 is less than x is less than or equal to 8, which essentially means that you start at the number above 4 for your natural numbers, which is 5, because there's no equality here. You go up to 6, 7, and you actually include 8 because you do have this equal to portion right there. I think we're getting the trend. So, let's see. Example 7, representing sets of natural numbers. Express each of the following sets using the roster method. We've got x, such that x is an element of the natural numbers, and x is less than or equal to 100. Now, if I look at the solution here, and I do this in the roster method, if it's less than or equal to 100, I'm going to start with my smallest element, which is 1, and I'm going to work my way up. Okay, so I'm going to go 2, 3, 4. I can work my way all the way up to 100 because it is equal to here. I have that little equal to sign right there. But I can't go past 100. So our set here is 1, 2, 3, 4, all the way to 100. And every natural number in between. If I look at B, x such that x is an element of the natural numbers, and 70 is less than or equal to x is less than 100. What this tells me is that the smallest element of my set here is 70. I count up because I'm using the natural numbers here all the way until I get to the number that's actually before 100, which is 99, because we're not equal to 100 here. So I'm basically going all the way up to 99, and that's what's in my set. 100 is not in my set here because I don't have an equality on the 100. And that's why you see the set 70, 71, 72, 73, all the way up to 99. Let us look at another definition here. Cardinality and the equivalent sets. The definition of a set's cardinal number is the cardinal number of set A represented by n of A is the number of distinct elements in set A. The symbol n of A is read n of A, which means the cardinal number of set A. Repeating elements in a set neither adds new elements to the set nor changes its cardinality. So let's look at the following sets. It wants us to find the cardinal number of each of the following sets. Basically, the way we would do it, we would write n of A, which means the cardinal number of A, equals, okay, how many numbers are in this set, or how many things are in this set? I've got 1, 2, 3, 4. I have 4 things in this set, so the cardinal number of the set is 4. Boom, that easy. If I look at set B contains 0, and that is the only thing it contains. So the cardinal number of B is 1, because it contains one thing, and that one thing is 0. Remember, 0 is not the empty set. 0 is something, and we have to count that something. So our one solution here is essentially what we're counting, and that solution is that 0, and that's why the cardinality of B is 1. If I look at the set C that goes 13, 14, 15, all the way up to 22, 23, basically includes all natural numbers between 13 and 23, I need to find the cardinality of C. The cardinality of C. All numbers between 13 and 23. Let's count that. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That's 11 elements. There's 11 elements in this particular set. I do encourage you to count, because if you would have just subtracted the two numbers here, you would have come up with 10. 23 minus 13 is 10. But if you actually count the elements in the set, you do indeed have 11. So take your time. Don't take shortcuts. Let's try to find the cardinality of the empty set. Remember, this is the symbol for the empty set. The empty set contains no elements. Therefore, if I were to write the cardinality of the empty set, that would be 0, because there's nothing in it. So the empty set contains no elements. So the cardinality of the empty set is 0. Let's define equivalent sets. The definition of equivalent sets is a set A is equivalent to set B, means that the set A and set B contain the same number of elements. For equivalent sets, the cardinality of A equals the cardinality of B. Now, equivalent is not the same thing as equal to. If you notice, the only thing equivalent means here, truly, is that the cardinality of each set is equal to each other. So, let's look at an example of equivalent sets. Remember, equivalent is not the same thing as equal. If I see set A here, set A is X such that X is a vowel. If I list all of the vowels, that's A, E, I, O, and U. If I look at set B here, B is the set of X such that X is an element of the natural numbers, and 3 is less than or equal to X is less than or equal to 7. So if I wrote that in my roster notation, I would have that set is 3, 4, 5, 6, and 7. These are two equivalent sets because, as you can tell here, the cardinality of A equals the cardinality of B, which is 5, because there are 5 elements in each of these sets. 1, 2, 3, 4, 5. 5 elements in this set. 1, 2, 3, 4, 5. 5 elements in that set. They are equivalent sets. Remember, equivalent does not mean equal to. It just means that they have the same number of elements in each of those sets. The lines with arrowheads up and down, just like so, indicate that each element of set A can be paired with exactly one element of set B, and each element of set B can be paired with exactly one element of set A. So essentially, this pairing that we've done here with these lines shows that each element can have exactly one pairing with another element in each of those sets, helping further prove that they are equivalent sets. So that's what we call a one-to-one correspondence and equivalent sets. If set A and set B can be placed in a one-to-one correspondence, basically just like it is here, where we have one element going to strictly one other element, so 3 goes to A, 4 to E, 5 to I, 6 to O, 7 to U. If we have that direct one-to-one correspondence, then A is equivalent to B. Therefore, meaning the cardinality of A is equal to the cardinality of B. If set A and set B cannot be placed in a one-to-one correspondence, then A is not equivalent to B, in which case the cardinality of A would not be equal to the cardinality of B. If we look at example 9, it says determining if sets are equivalent. The figure shows the top 5 impediments to academic performance for U.S. college students. We want to let A equal the set of 5 impediments shown in the figure. B is going to be the set of the percentage of college students reporting each impediment. And we want to know, are these sets equivalent? And we need to explain this. First, we need to line out what set A and set B even are. Set A is the set of 5 impediments shown in the figure. So, set A are essentially all of these impediments here. This is our set A. Set B is the percentage of college students reporting each of these impediments. So, this, or these collection of percentages here, would be set B. Follow me? So, if we look at this and we set them up in our roster notation, we would see that A is stress, sleep problems, illness, anxiety, and work, while B is the set 28, 20, 19, and 14. Now, when we write sets, just a reminder, when we write sets, we do not repeat elements. 19 was twice in this set, but we only write it one time when we write it in the roster notation. is essentially only needed to be written one time. Okay, so we do not repeat elements when we write them in our notation. We only write them one time. So, after we've written these, we can try to set up a one-to-one correspondence with our arrows. We can see that stress is indeed the 28, sleep problems is the 20, illness is 19, anxiety is 19, and work is 14. So when we set up this correspondence between these elements, stress is the 28, sleep problems is the 20, illness is 19, anxiety is also 19. Uh-oh, got a problem. Work is 14. What we see here is there's not one-to-one. We've got somebody sharing here, sharing this 19. So, solution. The lines with the arrowheads between the sets in the roster form indicate that the correspondence between the set is not one-to-one. The elements illness and anxiety from set A are both paired with the element 19 from set B. These sets are not equivalent. It is very key here that you do not accidentally write two 19s here. You only write an element in a set one time. Even if it's repeated 10,000 times, you still only write an element in a set one time. Once it's represented, it doesn't need to be written multiple times. If you rewrite it multiple times, you could potentially wind up with something that looks like a one-to-one correspondence, but isn't. And this would be wrong. Okay, so we only write it one time so that we do not make this mistake. This is correct to show that there is not a one-to-one correspondence. Gotta be careful there. Only write an element in a set one time so that you do not mess up whether or not there's a one-to-one correspondence. You could also check to see if there's a one-to-one correspondence by looking and counting the elements in each set and checking the cardinality. Because for there to be a one-to-one correspondence, the cardinality has to be the same. Here, if we look at the cardinality of set A, the cardinality of set A is 5. Because we have 5 things in set A. 1, 2, 3, 4, and 5. If we look at the cardinality of set B, we only have 4 things. 1, 2, 3, 4. Because those cardinalities are not equal, then we know that the sets are not equivalent. So because the sets do not contain the same number of elements, they are not equivalent. Let's look at finite and infinite sets and finally give that a definition, because we've been throwing some of those words around the entire class. A set A is a finite set if the cardinality of A equals 0. That is, A is the empty set. Or the cardinality of A is a natural number. So if you wind up with either of these cases, if you wind up with the case where the cardinality is 0 or the cardinality is a natural number, then it's a finite set. A set whose cardinality is not 0 or a natural number is called an infinite set. So basically, I'll make this real simple. If you can count the number of elements in the set, it's a finite set. If you cannot count the number of elements in a set, it's an infinite set. A finite set would be like the set 1, 2, 3 that has 3 elements. You can count those 3 elements. Or if you gave this a name, you would say the cardinality of A equals 3. If you had another set B, which was X, such that X is in the natural numbers and X is greater than 2, that set, if you wrote it in roster notation, would be 3, 4, 5, 6, and it would continue on forever. And you couldn't count the number of elements in that set because the number of elements in that set is infinite. So there are infinite elements. and they cannot be counted. This is what's called an infinite set. This is a finite set because I can count the number of elements in it. This is an infinite set. Alright, let's look at equal sets. Remember, I told you that equivalent sets are not the same thing as equal sets. So, set A is equal to set B means that set A and set B contain exactly the same elements, regardless of order or possible repetition of elements. We symbolize the equality of sets A and B using the statement A equals B. So let's look at this and determine whether sets are equal. It says determine whether each statement is true or false. We have the set 4, 8, 9, and we have the set 8, 9, 4. Are those equal? Yes, they are, because order doesn't matter. This is a true statement. If I look at the next set, I've got the set 1, 3, 5. Is that equal to the set 0, 1, 3, 5? It's not. It's not at all equal. They do share some elements, but they are not equal. This is a false statement. This set has an extra element, that element 0. That's what makes this not true. So the first set is equal, the second set is not equal. Okay. Now, the difference between equal and equivalent, I'm going to say it one time. Equal sets have exactly the same stuff in it. This has a 4, this one has a 4. This one has an 8, this one has an 8. This one has a 9, this one has a 9. They have exactly the same elements. They don't have to be in the same order. If I had another set and it was 7, 8, 9, all three of these would be equivalent. All three of these sets, if you called this one A, this one B, and this one C, they would be equivalent. But C is not equal to either A or B. Does that make sense? So equivalent just means they have the same number of things in the set. But remember that equal means they have the exact same elements in each of their sets. That is the difference. Don't get equivalent and equal to messed up. I hope that everybody has learned something today. This has been a little bit longer of a lecture than what we started with, but we're building our knowledge and our base of learning. Please go online, attempt the homework for Chapter 2.1. If you have any issues or any questions, do not hesitate to reach out to me. Y'all have a good afternoon.